How would you teach a computer to find the square root? It can't intuit the answer the way you might, but it can try every possibility faster than you can blink. That brute force strategy has a name: guess and check. Guess and check, also called exhaustive enumeration, works like this. Given a problem, we guess a value for the solution, then test it. Does this guess solve our problem? If it does, we're done. If it doesn't, we make another guess and keep going until we run out of values to try. The outcome is one of two things. Either we find a solution or we exhaust every candidate and conclude we didn't find one. That second outcome is subtle. Failing to find a solution doesn't prove none exists. It only means that among these particular values we checked, none worked. Suppose we want to know whether 7 is a perfect square. We could just guess randomly. Try 6, not the root, try 9. Not it. Try 2, no, try 0. Obviously not. We could keep flailing like this forever, but it's wasteful. Computers are pattern machines. Remember how range starts at 0 and marches upward in a fixed pattern. We want to harness that. Instead of guessing randomly, we'll be systematic. Start at 0 and count upward, one value at a time. That way we exploit exactly what computers do best, doing repetitive work fast. Case 1, the number is a perfect square. Say our number is 4. We start with a guess of 0. Does 0 squared solve our problem? 0 squared is 0, which is not 4, so increment. Now guess 1. Does 1 squared solve it? 1 squared is 1, still not 4. Increment again. Now guess 2. Does 2 squared solve it? 2 squared is 4. That matches. We're done, and the square root is 2. Notice the pattern. Each step we square the current guess and compare it to 4. As long as the square is less than 4, we keep going. The moment it equals 4, we stop with a hit. Case 2. The number is not a perfect square. Say our number is 10. We use the same systematic approach, but now we need a little algebra, or we risk looping forever. Guess and check needs a finite set of candidates, so we need a rule to stop. The rule is this. Stop the moment our guess squared becomes bigger than the number. Watch. 0 squared is 0, which is less than 10. Keep going. 1 squared is 1, less than 10. Keep going. 2 squared is 4, less than 10. Keep going. 3 squared is 9, still less than 10. Keep going. 4 squared is 16, which is greater than 10. Stop. We never hit 10 exactly, so 10 is not a perfect square, and we don't need to check 5 or 6 or beyond, because their squares are only bigger. Here's the code. First we read a number from the user and call it x. We set guess to 0, then comes the while loop, whose condition is our stopping rule. Keep looping while guess squared is less than x. Inside the loop, we do one thing, increment the guess by 1. So guess climbs 0, 1, 2, 3, as long as its square stays below x. Eventually, the condition turns false. That happens when guess squared becomes greater than or equal to x. But greater than and equal to are two very different outcomes. If guess squared is equal to x, we found the perfect square. If guess squared is greater than x, we overshot. So x is not a perfect square. That's why, right after the loop, we add an if-else. The if checks whether guess squared is equal to x and prints the root. The else prints that x is not a perfect square. There's a catch. This works for any positive number, however large, but it breaks on negatives. Watch y with -2. Guess starts at 0. The loop asks, is 0 squared less than -2? 0 squared is 0 and 0 is not less than -2. The condition is false from the very start, so the loop never runs even once. Then the if-else checks. Is 0 squared equal to -2? 0 is not -2, so we land in the else and print that it's not a perfect square. That answer is actually correct, since negative numbers aren't perfect squares. The loop simply skips itself. Returning -2 is not a perfect square is technically right, but it's a bit blunt. Maybe the user just slipped and typed a minus sign. We can be friendlier by wrapping a little extra logic around the code we already have. We introduce a Boolean variable, neg flag set to false. meaning we assume the input is positive. We read X, then check. If X is less than 0, we flip neg flag to true. The original guess and check code stays exactly the same in the middle. Then at the very end, we check the flag. If neg flag is true, the user gave a negative, so we add a friendly follow-up. If it's false, we do nothing extra. The flag simply remembers what kind of input arrived. Let's run it and see. Give it 4. The loop climbs to 2. 2 squared is 4, so it prints square root is 2. Give it 9. The loop climbs to 3. 3 squared is 9, so it prints square root is 3. Give it 10. The loop stops at 4. 4 squared is 16, which overshoots, so it prints 10 is not a perfect square. Now give it negative 4. The loop never enters, so it prints negative 4 is not a perfect square. And because neg flag is true, it adds a second line. Just checking. Did you mean 4? The friendly follow-up appears only when the input was negative. For positive inputs, the flag stays false and then nothing extra prints. Step back, and the big idea is simple. We can't test an infinite number of values, so guess and check needs a clear stopping point. Here, that point was the moment our guess squared exceeded the target. Be systematic, define when to quit, and handle the awkward edge cases like negatives. That same shape, enumerate candidates and know when to stop, is the backbone of brute force problem solving across all of computer science. To practice what you just learned, this course has free exercises and AI graded feedback on ludium.ai. The link is in the description.